So, hi there, and welcome back to the second part of the analysis of planetary gears. And if you're ready, we get started right away. As you remember, we can split the analysis up in 5 different steps. First of all is the rotational speed analysis. Then we have the torque analysis disregarding any losses. We have a power flow analysis. We include the losses in the torque analysis, and finally we can have the efficiency calculations. Now, the angular speeds. Well, if you recall from the last recording, we define a number of positive speeds, the omega 1, 2, 3 and A, indicated here by the arrows. So that means that all these rotational speeds are assumed to be initially positive, indicated by this direction. I can see if I can get this arrow. Okay, here you have the positive directions on all of these angular speeds. You must also remember that in this case, for the planetary wheel, it can rotate around its own shaft because we have bearings between the wheel and the shaft which it's sitting on, and you can also have a rotational motion with the planet carrier in this direction, rotational speed, indicated omega 1. You can also see that we indicate the planet carrier shaft with 1, the sun wheel shaft with 2 and 3, and the planetary gear with A. This is just an example or an illustration of what type of speeds you can get. In this case, where you have the low gear, you hold either the inner or the outer sun wheel still. You have an input on the inner sun wheel shaft or the outer sun wheel shaft, and then you have a rotation of the planet carrier shaft in this positive direction. If you then look at the high gear, here you lock the planetary gear shaft to the inner sun wheel or the outer sun wheel, which means that all of this will rotate with a uniform speed, that is, you have no relative motion whatsoever in the gear meshes. And then finally in the reverse gear you have you keep this shaft standing still, the planet carrier shaft, and you rotate on the inner sun wheel, and then you have a rotation in the opposite direction on the outer sun wheel, and that's how you reverse the rotational speeds. Now if we want to have an analysis and have some equations describing this, we can think of it this way, that you have a planet carrier rotating with the angular speed of 1, and you have all the other shafts rotating with their speeds. Now if you subtract the angular speed omega 1 from all the other angular speeds, you will have an equation looking like this. And if you compare this equation to what you had for a simple spur gear, an internal or external spur gear, you can see the resemblance. If you divide the rotational speeds, you get the expression for the gear teeth, and you can have a plus sign when you have an internal spur gear, meaning that they rotate in the same direction, or you have a minus sign, meaning that they rotate in the opposite direction for the external spur gear. And by writing these type of equations, you can determine all the unknown speeds, and in order to do so you must of course prescribe some of the rotational speeds. And it turns out that if you have n shafts in the planet gear, you can write n-2 equations, and then the rest 2 remaining speeds you have to prescribe from start. This is an example of how this similar such a gearbox can be designed. This is a rather, well, complex, you might say, gearbox. You see that you have, this is a planetary wheel with two gear races. One is there, one is there, and you also have a planetary wheel here. So that means that you have a rather complex mesh between these different gears. And in this way, by locking some of the shafts and having other shafts free, you can have different output speeds on shaft 4. For example, the first gear, when you lock shaft 1 and you have shaft 2 free. Second gear, you lock shaft 2 and you have shaft 1 free. Third gear, you lock shaft 2 to shaft 3, which means that they can't rotate relative to each other. And then finally the reverse gear, you have shaft 2 as the input shaft, you lock shaft 1 and you let shaft 3 rotate freely. Then you have reverse output on shaft 4. And this you can solve this by if you look, for example, on the if you prescribe the shaft on the in shaft, or the speed on the in shaft, you can calculate by similar equations which I just showed you the shafts on all other shafts. But of course you must know that which shaft is to be free and which is to be locked. And how do you lock shafts? Well, you do that, for example, by brakes or by clutches. Okay, so let's start with an example. This is a planetary gear of a four-wheel type. You have two sun wheels there, and you have two gear races on the planet wheel. One is there, one is there. We prescribe the positive direction on all the shafts, the first sun wheel and the second sun wheel, and also the rotational speed of the planet wheel, as well as shaft 1. And shaft 1 here is a planet carrier shaft. Remember that that is the shaft speed that we reduce every other speed with. Okay, we should determine the outgoing speed of shaft 1. So this is a planet carrier shaft. And the outgoing shaft has a brake torque of 30 Newton meters, and the input shaft N2 has a speed of 1500 RPM. So this means that this shaft rotates with 1500 RPM, and we are interested in finding the output shaft speed here. Okay, we also have a number of gear teeth given here for the different gear wheel, and of course we also have the gear efficiency given, but that will be we won't bother about that right now. We'll do that when we come to the torque analysis. Okay, so just to have a look at the nomenclature, we have 1, 2, 3 and A, the same way as I described previously. So how many equations can we write then? Well, the number of shafts is 3, so that means that we can write 2 equations. We have first of all to compare the speed of one of the sun gears with the planetary gear, and we can see that ratio, if we reduce it by omega 1, we have the same ratio as the gear wheels involved. That is the sun wheel here and the planetary gear here. You can also see that as a kind of a little rule, that if we have the index 3 here, we should always have the index 3 here, and vice versa. For the planet wheel we have the index A, and then we have the planet gear wheel here, index 13. The same goes for this equation where we compare the speed of sun wheel number 2 with the angular speed of the planetary wheel, and in the same way we write this as a ratio between the gear teeth. Here you have a minus sign in both cases because both of the gears are external gears. Now you can eliminate omega A and you end up with an equation looking like this, which we then can solve because we have a number of input prescribed. We know that the input shaft is running at 1500 RPM. We know that shaft 3 is standing still. So we can then calculate the output speed, and we have that here, where the output speed will be then minus 1200 RPM, and this minus sign then indicates that it does not rotate in the assumed positive direction but in the other direction. We can also calculate the speed of the planetary wheel, and that will rotate in a negative direction with 3000 RPM. So what we can conclude then is by prescribing two of the speeds, the 1500 RPM input and the now shaft 3 standing still, we can calculate the output speed minus 1200 and the rotational speed of the planetary wheel. Okay, so if you like, you can of course also compare this if you have simple spur gears, an external gear and an internal gear, just to see the resemblance of the equations. In this case for the external gear, and here you have for the internal gear. And you can compare it to the previous equations and see that they are very much similar. Okay, so that concludes the part 2 then, the omega analysis. And hope to see you in part 3. So that's all for today. I hope that you have got a good insight in the omega analysis and hope to see you in the next clip, the video clip, where we will start going through the torque equations. Okay, see you then.